Imagine you have a long chain of carbon atoms, and at the very end, there's a carboxylic acid group, that familiar arrangement of a double-bonded oxygen and an OH group. Now, what if I told you there's a way to simply snip that last carbon right off the chain and replace it with a halogen like bromine?
In the world of organic chemistry, losing a carbon atom is usually a difficult and messy process. But in the 1800s, Clotilde and Heinz Hunsdiecker popularized a method that does exactly this with surprising elegance. Today, we call it the Hunsdiecker reaction. Let's look at the starting ingredients on our screen. We begin with a silver salt of a carboxylic acid. Notice the oxygen at the end isn't attached to a hydrogen anymore. It's bonded to a silver atom. When we introduce a halogen, typically bromine, something interesting happens. Watch what happens when these two meet in a solvent like carbon tetrachloride. The silver atom has a massive crush on the bromine. They find each other irresistible. As you can see, the silver and one bromine atom immediately link up to form a solid precipitate, silver bromide, which falls out of the solution. This leaves us with an unstable intermediate, an acyl hypobromite. But here is the key insight. This intermediate is incredibly twitchy. The oxygen-bromine bond is weak and it wants to break. Under the influence of a little heat, that bond snaps perfectly in half. Let's visualize this at the molecular level. This is a radical mechanism. Instead of the electrons moving in pairs, they split up. One electron stays with the bromine and one stays with the oxygen. This gives us two highly reactive species called radicals. Now, look closely at the carboxyl radical left behind. It's holding on to a single electron and it's desperate for stability. The easiest way to find that stability? It's to let go. The molecule rearranges and that terminal carbon-carbon bond breaks. The carbon and those two oxygens float away as a stable molecule of carbon dioxide. Notice what's left. Our original carbon chain has been shortened by one, and it's now a carbon radical searching for a partner. And who is still floating around in the mix? That bromine radical we created earlier. They find each other, snap together, and just like that, we've transformed an acid into an alkyl bromide. So, why does this matter? Well, think about the geometry of what just happened. We started with a carbon chain of length n, and we ended with a chain of n-1. In synthetic chemistry, being able to shorten a chain while simultaneously adding a functional handle like bromine is like having a pair of molecular scissors and a glue gun at the same time. The Hunsdiecker reaction reminds us that sometimes, to build something new, you first have to be willing to lose something, even if it's just a single atom of carbon. It's a classic example of how radical chemistry can take a stable, boring acid and turn it into a versatile building block for the world of tomorrow.